Welcome everybody to this presentation on breakthrough DOE tools for elastomer science and technology. I'm Mark Anderson. I'll be presenting today from Florida in my home there, and welcoming the Latin America Society of Rubber Technology that have come in per Juan Cabrera. Buenos dias. If you can hear me and see the presentation on your screen, take a look at your GoToWebinar control panel and press that raise hand button. All right, Rich, TK, etc. Thank you. Okay, that gives me the feedback I need to know that I'm making it through the vast internet. So let me start my presentation. We'll provide a series of case studies that illustrate the application of these DOE tools for the elastomer science and technology, rubber and such. As I said, my name is Mark Anderson. I'm a professional chemical engineer, certified quality engineer, etc. I'm very well versed in design of experiments based on experience in many industries, but primarily the chemical process industry. So I rely on you for the subject matter knowledge to make these tools work. But what I want to do is just provide some good ideas that could prime the pump, so to speak, so that you'll make better use of these multi-factor tools. As I go through, I'm going to keep you on mute just because of the issues of voice over internet protocol and reverberations and things like that. If you throw in some chat, I might see it during the presentation, but most likely I won't get to it till the very end. But I'll try to address any questions that come in on chat. If you have further questions and anything more complicated, I would encourage you to send questions after the session to my email, mark@staties.com. The presentation will be posted, the slides and also the recording afterwards, to our website, www.staties.com, and there's a couple ways you can get to this webinar's page from the home page, or follow this link. So again, I'll try one more time just so we get you in the habit. I'm going to put the hands back down. If you're still with me, hands back up. Right, and so one of the questions that came in was about the video not being able to attend. So just hang in there for a couple of days and the video should be posted up. And please get back to me, one way or the other, whether you're here live to listen to my presentation or you come in via video. Feel free to get back to mark@staties.com. Okay, I think we're in good shape. I'm going to go ahead and put the hands back down again. And we'll take a look at my mission today, which is to really promote the idea of multiple versus one factor at a time presentations. And we like to call this one factor at a time approach the OFAT, O-F-A-T. And this is the standard scientific method. And that's what I'm trying to get people off of. And using design of experiments tools, you can do multiple factors or multiple components. And so I'll be illustrating that for the elastomer type applications with a number of different case studies that cover basic aspects of design of experiments, including factorial design for screening and characterization, response surface methods for optimization, and then particular tools for mixture where you can optimize formulations. And then finally, combining mixture and categorical, you can also combine in process factors and do all sorts of combination designs. So let's start with an opener here, which is a very famous case that was presented by George Box in Quality Magazine, and it involves the application of multi-factor approach versus the OFAT to improve the bearing life, which is shown here from a company called SKF, which is based in Sweden. Their problem was that Japanese manufacturers in the 70s had come up with new designs that increased the life tremendously at similar or lesser costs. So the engineers in Sweden were tasked with taking a baseline accelerated life of 17 hours and try to get that more than doubled up to a total of 40 hours at the very least. Otherwise, they would go out of business. Now, when these engineers started, they didn't know any other way other than one factor at a time. So they simply changed the first factor that they thought was going to be most important, which was related to a heating type factor. And they went from low to high on that one factor, and they got an increase, but it wasn't enough to meet the goal. So then they turned their attention to a second factor, which is labeled B, and this actually was the oscillation of the bearing, which is the kiss of the bearing to the cage. And when they did that, from low to high, they got an increase again, but it wasn't enough. It wasn't enough to meet the goal. So again, that failed. So then the next thing they did was they went to the third factor, which is C, that's going from the front to the back, and they changed that one. That one was actually a categorical factor, and the original raceway of the bearing was metal. And actually you can see in the picture that they switched to a plastic raceway. However, just switching that metal to plastic made a very small difference. It certainly wasn't enough on its own. So that was that. So then what happened was they sent an engineer, Christopher Hellstrand, to Wisconsin to study under George Box, who at that time was at University of Wisconsin in Madison. And he learned about a technique called two-level design, which is represented by the number 2 to the power of 3 in this case, where 3 is a number of factors, and of course 2 is a number of levels. So if you do the math, 2 to the power of 3, of course that makes 8 combination or 8 runs, which were run in random order back in Sweden, and lo and behold, they found there was a combination which was actually the A-B interaction, the combination of the heat and the oscillation, that made all the difference, and that created a breakthrough in the life and succeeded in further trials to make all the difference and keep SKF in business and beat the competition. So that's a great story, and it really shows you that you don't want to do the one factor at a time approach. You always want to go after this multi-factor DOE approach. Whenever you're getting close to making a breakthrough like this, you have to start thinking about the possibility of interactions. However, there's a more subtle advantage to the two-level design, and it has to do with the efficiency of doing this. So I'm going to erase off all my scribbles here, and I just want to point out that on the right side of this cube, we actually have 4 conditions that are at the A+, right? And at the left side of the cube, we have 4 that are at the A-. So we have an advantage of 4x4 comparisons. Obviously, sample size 1 is always to be avoided, and I would recommend whenever you do an experiment to have at least 4 that you average out when you do a comparison, even a simple t-test comparison. So the engineers, to match that, could have done 4 at the baseline and then 4 at the A+. However, we then can turn our attention to B, and we can point out that the top of the cube, which is B+, has 4, and the bottom, which has B-, has 4. And so we have another 4x4 comparison, and that's forcing the OFAT experimenters to do another group of 4 at the B+ level. But then finally, C is going from 4 in the front to 4 in the back. So finally, when all is done, to get the same power of sample size 4, the OFAT has to do 16 runs versus there's only 8 in the 2-level. And this has to do with the fact that we're working in a parallel type of processing scheme. And so obviously parallel processing is more efficient than serial processing. So we get an advantage both in the ability to be able to see interactions of things and also in terms of the efficiency. So we're good on both counts. Now what I want to do is go to the program and I want to demonstrate how the software works. But before I do, let's just ask if you're with me so far, if you could see the advantage of doing the multi-factor versus the one factor at a time. Put the hands up again on your screen so I know that you're able to see my point. All right, Daniel, Hugo, Juan, Kevin, okay, I'm getting lots of positivity here. Thank you very much. So I'm gonna put the hands back down. So now we're gonna go over to Design Expert. And I'm gonna go ahead and open up this case that has bearings. And I'm gonna rebuild it so you can see how this is built and how easy it is to use Design Expert for this, which is a dedicated program for design of experiments. So what we have here is a design builder that has a white diagonal that are all the possible combinations, or what we call full two-level factorials. Now with only 3 factors, you're certainly going to want to just do the full factorial. There is a possibility of doing a half fraction, but you can see by the red coding that we don't recommend this. The resolution gets so low that you end up aliasing all the main effects of 2-factor interactions. However, once you get to 5 factors, which was a common design I would run in process development, things like time, temperature, concentration, stirring rates, things like that, you can, with 5 factors, cut it in half. And you can see this is a green design. This is what we call a high resolution or characterization design. So I would encourage you to consider doing fractions. Now, another possibility would be if you just want to screen factors in a first stage and then do a follow-up characterization, you can go all the way up to 8 factors, for example, and you can do a 16-run design that still will resolve main effects clear of any 2-factor interactions. And then before we press ahead, I should mention, and we also have more advanced modern designs that can give you minimum runs, so that if you go to 9 factors, for example, and you would have to do at least 32 factors to do a screening, you can do this minimum run screen, and you're able to then get down to only 20 runs, even putting 2 extra runs in, versus with the regular 2-level, you'd be forced to do at least 32. We also have, for example, with 9 factors, the ability to characterize, which would be a higher resolution in only 46 runs, whereas it would take 128 runs to do the high resolution characterization. So we have some pretty good options, but this one is a very simple 3-factor design. We just do all the possible combinations. Normally I would consider putting some center points in, particularly for numeric factors, but no, they just did this really easy 8-run design and entered in these factors of oscillation. I guess that actually was the bottom factor. And then the factor on the side was the heat. And then the factor from front to back, as I said, was the cage design, metal to elastomer. I'm going to say elastomer because my presentation is, aimed at elastomers, but it may have been actually some sort of plastic. Okay, then normally we would do a power calculation, and we would consider what their goal is at a minimum to get to 40 hours of life. However, they would have been happy to get some increase in the life, maybe, let's say, even a 10-hour difference in life would have been advantageous. And let's just say that the normal variation of a bearing for life would be, let's say, 2 hours. And by putting in the difference you're trying to detect for your experiment and the variation, you can create a power calculation, which is very handy for Design Expert. Now, in this case, the 8-run design succeeded because they were looking at very strong factor level differences that would generate, fairly big differences in their response. And so the 8-run design was adequate. So now we have our recipe sheet, which is laid out in a randomized plan. And this is one of the keys to doing good DOE. Now I'm going to go ahead and pull in the results. And the first thing I'm going to do is observe through a sorting mechanism that we have a tremendous increase in life throughout the course of this experiment. In fact, it's almost too good to be true. Some of the results are so high that they looked almost like they were outliers, that they were aberrations. We can use graph columns tools in Design Expert to take a quick look at the main effects of the oscillation, which made a big difference, the heat, which made a big difference, and then the cage design didn't seem to make much of a difference, but possibly a small increase on the life. So this is a pre-analysis. Now we get into the actual analysis of this. We start the analysis at this point without a transformation, and we use a very specialized graph called a half normal that has the standardized effect absolute value, which is basically the absolute value of the effect. And keeping our eyes on the prize, we click the one furthest to the right, which we already saw was oscillation being a big effector. The next one is the heat. We saw that on the graph columns. But then there's this very big interaction of A and B that also stands out. And these other effects that are off to the left that are near zero, that are involving the cage, are so small that they're probably just a measure of variation. And we know that because of the specialized y-axis, which is called a half normal paper. And you may be familiar with probability paper. It's something that's used oftentimes to characterize normal distributions. So this half normal effect plot is very useful for picking out effects. You're looking for the ones off to the right, and then leaving the ones that are near zero that are pretty much lined up, into the what we call the error pool. Now we can look at this on an ordered bar chart called a Pareto, which I like. And this one has a standard t-value limit here. And the ones that I've picked, the effects that I've picked, are above the t-value at 0.05 risk or 95% confidence. Now they don't quite make it to this more properly pairwise corrected limit of Bonferroni, but even so, they do definitely stand out. And if we were to look at the analysis of variance, we would see that the p-values are quite strong, as you can see here, all the way through. They certainly meet the 0.05. And we've got very good fit statistics, they're indicated over here in this report from Design Expert. Now, what's interesting about this case study is that the results were so good that it appeared that a few of these results went outside of these red lines on the residual versus run plot. And that's why they're highlighted, and they turn out to be the two high results. Well, luckily, there's a remedy for this, and it's provided by a specialized plot called Box-Cox that will look at the results and recommend different types of transformations, and a very common one is called the log transformation. So when you have a very big increase, like more than 10-fold in the response, like we have here, or nearly 10-fold, log is oftentimes very effective. So I'm going to use a feature in Design Expert 13 that allows us to do a second analysis. And this one I'm going to transform using log. And you can either use base 10 or natural. I'm going to use the base 10. And when we do that, we get even more of a separation of these three off to the right, and even higher results, on this ordered bar chart or the Pareto, even going above the more conservative pairwise Bonferroni. And this produces even better p-values and even higher fit statistics. And then it ends up giving us really good results for the very powerful diagnostics. And one of the big things is we no longer see those two high results being flagged as being outliers. They're all within the red line. So that's the end result then, and you can look at this model graph interaction, and you can see that the effect of the oscillation, which is a kiss of the bearing to the cage, when oscillation is changed at the low heating level, it makes no difference, as you can see by the overlapping least significant difference bars on this red line. But when you increase both the oscillation and the heat at the same time, you get this tremendous increase that stands above everything else. And so that's our finding here for this multi-factor two-level design. And it gives you a really good result, as you can see with this towering green bar at the back end here. All right, so as I said, what I plan to do is at the end, I will ask if there's any questions. So I don't see any questions coming up yet. So maybe just make a note of your questions at this point and be ready to ask me later, and I can come back to this case study. But if you can see the advantage of the two-level design, particularly with this bearing life case, give me back some positivity again by pressing that raise hand button. Okay, TK, thank you. Jose, Kranti. Okay, that looks like a pretty good sampling. I'm going to take that as a positive, put the hands back down, and that'll be the end of our first case, which is illustrating the factorial design in general for this bearing. And then the rest of the story is listed here, is that they were able to actually increase the bearing life from 41 million up to 400 million revolutions, and they reduced the cost by putting that plastic in. And this was documented in a US patent and also in this design engineering from 2000. And what George Box said in a book that he wrote, or article, Improving Almost Anything, Ideas and Essays, Krister showed that they could test 2 additional factors for free without increasing the number of runs and without reducing the accuracy of their estimate of the cage effect. So what a win that was. So I always like to show that case study as an inspiration. Now I do have another 2-level design that I was involved with a company based in Minneapolis called Robinson Rubber, and they were working on this 3M part. As you know, 3M is based in St. Paul, Minnesota, and the problem was that this rubber was not bonding very well to this metal. It was actually for a sander, and so they were having a little trouble with that, and they were getting a great deal of scrap. You know, it was more than 10%. So with help from me and Staties and the use of our software, over a 2-day period that they blocked day by day, blocking being a good technique to remove a known source of variation, they tested the vulcanizing temperature, the bond material, which is a categoric. This was not revealed, it was kept confidential what the bond material was, the bond thickness in terms of 1 or 2 coats, injection pressure, and then the bond settling time from 1 to 120 minutes or 2 hours. For responses, and you can do many responses, but the focus was on 2 main ones, whether they were getting inadequate cure, if that was the cause of the fraction defect, or if the problem of the defects was due to the low bond, which was poor coverage of rubber on the metal. And this was published in Rubber and Plastic News in 2008. I wrote this up as a case study, and it's available on our website. If you're interested, contact me and I can send you the link. So this one, I'm going to rebuild. Again, first I'm going to open up the file. So here's the final recipe sheet with the results entered in, but I'm going to go ahead and rebuild this so you can just see how this was done. All right, so this one, they couldn't do all in one day. And they had 1, 2, 3, 4, 5 factors. So they started off with this idea of doing all the possible combinations of 32 runs, and that was going to take too long. So they cut down to a fraction, 2 to the 5 minus 1, which is 1/2 fraction. But then when they switched to the blocking of one day versus the next, it actually took away a little bit of information, as you can see by the graying out, to account for that block difference. It created a slight amount of aliasing. However, when you look at the aliasing that's provided by Design Expert, you can see that main effects are aliased only with 3-factor or even higher interactions, which are not shown. And many of the 2-factor interactions are not aliased with anything other than 3-factor or higher. So this is degraded somewhat by the blocking, but it worked out just fine in the end. Here's where we enter in the names, units, the types of factors, the bond material being categoric, and then enter in the levels if it's numeric, and then the types if it's categoric. And then the blocking, this was done day by day, so you can enter that in. And then the responses, and normally I would do a power calculation, but in this case, let's just clear this out and press right ahead to the final results because we know that it was significant. But normally I would do that power calculation. So now I'm going to reopen the design. And I noticed that when I open this, there's actually one result that is ignored. So in the program, you can selectively ignore results. And the reason for that is that when we did the diagnostics on it, it turned out to be a true outlier. So we have one result that for some reason came out defective, and it wasn't expected that that would happen and couldn't be reproduced. So I'm just going to leave that out. Then when we look at the cure results, now this is fairly granular in terms of just using fraction defect. You're much better off using a count of defects per number of parts or using some measurement of things like cure if you can. And so that's a little bit hard to pick out, but let's just say we picked out the cure temperature, injection pressure, might be a good start, or maybe just the cure temperature. So it's a little bit uncertain on the results here, but that's how real life occurs. So I'm going to go with this. The A is fairly clear of any likely interactors. The program is telling me it's significant. Now we don't have as good of results as the textbook example I showed you with the bearings, but it was enough. Oh, okay, and then this one does show that the log is going to work better. So then I'm going to go back and redo this based on the box Cox and just see if this gives us a better result. Okay, that's not going to work because I've got some zeros in there. And we could try another transform the square root that would help. And let's just see if I can tease something else out of here. Again, I have the cure temperature. Let's see if this injection pressure with a slight modification works better. Let's look at the Pareto. So if you were to send this data to me or to our stat help at statas.com, we would help you with the results. And maybe we would see our way clear with your agreement that the injection pressure also makes sense. And so this would be the effective cure temperature. Higher cure temperature is reducing the defects, and lower injection pressure seems to be helping on the defects. So I might go that route. So what Robinson Rubber did is they used these results and made the changes, tempered by the subject matter knowledge, and they were able to get the defects down to pretty much zero. So now let's look at the bond. On this one, it looks like there's some factors off to the right here. However, because of the aliasing, this one is probably the BC interaction. So there's a way to substitute, more likely. It's unlikely that you would really see an interaction that didn't include both parents. So I made a little bit of a change to that one, and that seems to be making all the difference. And I'm just going to press ahead with this model, which is the bond material, bond thickness, the interaction of the two, checking diagnostics. Here again, it does look like we do better with some sort of transformation, but because there's some zeros in this, you can see that the data set is fairly meager, and yet we're getting some pretty interesting results. And I'll take the square root of this again, which is, going to help somewhat. And now we get this setup of families a little bit further out to the right. This AE, I would substitute in as BC. And this would be my final analysis, I think, that gives us the strongest results, some really good fit statistics. And so that's what I'm going to go with. And then we'll look at the BC interaction, and we can look at the effects of B, and we can look at the effects of C. And then in the end, you can go to numeric optimization. And you can minimize the defects caused by the cure and minimize the defects caused by the bond. And the program will dial up a solution that says go to the high cure temperature. We talked about that. Use bond material A, apply 2 coatings of the bond, reduce the injection pressure, and the settling bond mix didn't matter. So I would go with just the 1 minute because it's faster. And that gives us really good results in the end. So that's my second case. Again, I'm going to just check and see if any questions have come in. Nothing has come in yet, but jot down any questions you may have. Hopefully, if you're involved in the elastomer industry and working with rubbers and such, this hits the spot and showing you an actual success story. So if you like what you see so far, give me some feedback. Hit that raise hand button that you like it. All right, I'm getting some nice feedback here from Pablo and Mira and people like that. So thank you. I'm going to go ahead and put the hands back down again because we want to press ahead and show some more advanced design of experiments, as I promised. So let's move on to the next one. Okay, now we're moving ahead from 2-level design that's used for screening characterization primarily, where the focus is on effects that you see from your factors for a process, to a response surface design, which is used for optimization purposes. And this one I found from Journal of Rubber Research, as you can see at the bottom here, and I thought it looked interesting, so I brought this in and analyzed it in Design Expert. So in this case, the scientists were trying to produce a steel reinforced elastomeric structural bearing that would operate beyond a customer's required compressive stiffness, which is a CS, and meet the European standard for vertical deflection under maximum load, VDUML. Now this goes way beyond my, ability as a chemical engineer and starts to get into some really high powered, aspects of developing better rubbers and elastomers, and also into architectural aspects. But I'm for it because it sounds like it's something that would be really good to improve. So they determined that the cross-linking of the rubber was probably going to be the key, and that would be affected by these 3 variables of time, temperature, and pressure. And they did a specialized response surface method called a box-Bentgen. And this design is nice because it involves only 3 levels. Whereas normally the central composite design, which is the standard one for response surface, would take 5 levels. And I'll demonstrate that for you. But the box-Bentgen is actually pretty good for a 3-level design to do response surface. It's certainly a lot better than a full 3-level that requires many more runs. So it's kind of like a fractional 3-level design. So I would definitely say box-Bentgen is one of the top choices. So let's take a look at this. I'm going to close this out that I have up here. And now I'm going to open up this vulcanization design. And you can see I've been fiddling with this a little bit already. And I came across a result that was discrepant. And so just full disclosure, that particular result is being ignored because it seemed like it was causing problems with our fitting. So keep that in mind as I go along. I'm going to go ahead and build this so you can see where it comes from. So the normal design that we would use is called a central composite. It's comprised of a core factorial, which is specified by these lows and highs that are normally listed as minus and plus. And then you put points outside of the original cube to get more leverage. And the end result of it is something like this for the central composite design, or CCD we call it, would be comprised of a square with center points replicated, and then there's points on the outside that are represented by stars. But you can see you end up with 5 levels because going from left to right, we have the low star, the -1 level, the 0 level, the +1, and the high star, which is represented by the letter alpha. So the engineers and scientists here wanted to do only 3 levels, so they switched to this box Benken. And this one will only have 3 levels in it. So it's a good choice. It's not too bad. It's not quite as flexible for blocking and things like that. But I guess they were able to do the entire design all in one block. We normally would do more center points than 3, but that's what they did. I recommend doing 4 or 5. So here are, our inputs are typed in, very easy. Responses are listed. You can do any number of responses. Now, Design Expert makes this layout for you in random order. And so you just need to go through and do the work and collect the results and see what happens. So here are the results, and there's a range of results for the CS and a range of results for the VDUL that look somewhat promising. So we just press right ahead and do the analysis of this. And Design Expert will fit a series of polynomial models, starting with a linear fit, a two-factor interaction model, and it'll keep going as far as it can. The box Benken is designed to fit a quadratic, and that one, by the time you work up the fact that those quadratic terms are significant, and you get less of a lack of fit, and you start to get some decent results for R squareds, is the model that we pick. Now this one, if we look at the entire quadratic model, ends up with lots of terms that are not significant. So what I did on this one is I did algorithmic reduction based on p-values, and I went back from the full model and I started systematically taking out any terms that had alpha greater than 0.1, that were insignificant, at a 0.1 level. The program provides this option, and it starts systematically excluding terms, as you can see here, until it only has terms that are significant. So primarily in this one, we're seeing the A squared being significant. And then A is added to support the A squared. Now what I ended up doing, let's go back, and I'm just going to reopen this file again. So I'm going to close it, and I'm going to open it to reset the analysis. I fiddled with this a little bit. Oh, it looks like I did end up with A and A squared. Okay, so on this one is about the best I could do with it, and we get this one factor plot with the confidence bands on them, and that shows us that at the mid time we're able to get a much higher value for the CS. So that one, just one factor seemed to be affecting it. Let's see what happens with the second response. Suggested quadratic already. It looks like I did a model reduction, took a couple of terms out, and this one I get a much better fit. And I didn't see anything abnormal with it. And so here's a picture of the impacts. Let's see, under perturbation plot, I can see that C, steadily decreases the VDUL as you increase it, and then there's some nonlinear impact of A and B that's creating this interesting little set of contours. And then here's the 3D surface of it. So you can see that there's certain combinations that reduce this VDUL of the time and temperature, and let's see what happens with the pressure. That one has a steady impact on it, going less pressure, higher VDUL, greater pressure, lower VDUL. So then in the end, I think you want to maximize both the CS and the VDUL. And I entered in 190 at the minimum because that was a customer requirement that they had on CS. And then the European standard for the VDUL was 3.6. And so then we get our solution, and it's somewhere high temperature, low pressure, and you can actually see some things here in terms of where it's located, relative to the two different responses, where that flag is set. So let's say here's a flag and 3D surface. It's really just a function of A. You can see on this curved side. That's the only thing that really mattered for the CS. And for the VDUL, it was a combination of all three factors. And we want to set down here to get the combination of both the CS and the VDUL, above their minimums. So that is the response surface approach, which you would want to use, when you see nonlinear behavior after you've done screening and characterization, or possibly you may start right away with the response surface method if you know from your subject matter knowledge, that's probably what's going to be required. So make a note of questions and so forth. I'll come back to this later at the end. We'll have a little bit of time. But for now, you know the drill. I'm going to look for that hand being raised that you're with me so far before we move on to the next case. Okay, great. Edgar is raising his hand, and a few other people are along the way. You guys are great. Okay, so let's go on to the next case. And what do we have next? Oh, we've got a fun little example that I worked on with Pat Whitcomb, who is the founder of Staties and also a chemical engineer. And just for fun, I wanted to try doing a mixture design. We did this in our Staties kitchen, and I had to put this box around it because when the cross-linking occurred, it would start flinging this putty all over the place. And so the box was kind of containing the putty from getting all over our office. But basically what it is a chemical reaction, a cross-linking between a polymer, which is in white glue that's readily available, which is polyvinyl acetate, and a cross-linker, which is borax, which is easy to get at the local grocery store. And then you get this, result happening where water is precipitating and the properties are being changed quite a bit in terms of rebound and deformability. And having a background in rheology, we were kind of excited because this is what's known as a dilatant, which is actually non-Newtonian. In other words, it's not the normal type of reaction. And so it has really interesting properties when you stretch it, and that's why it's fun to play with. So using some information I picked up off the internet and through trial and error, we worked out that if we were to vary borax 1 to 3 weight percent, white glue 40 to 59, and water making up the rest of it, we could make up some fun play putty. And I ended up publishing this in Rubber and Plastic News in 2002 with an idea of showing that this mixture design of experiments is really powerful for optimizing formulations. So I'm going to bring that up on the program. I'll close out what's up here now, and we'll open up the play putty. This is one you can do at home. And to build this, we're actually going to go to a different tab. We normally would build this, well, it came up under this tab here, but normally it would come under mixture design, and you can see the ranges that are listed here with the total. I guess we did it in milliliters rather than weight percent. I've forgotten over the years now, some of the details of it, but that's how it was done. And there's actually a good start here with what's called a simplex lattice. If the ranges are all equal, that might work and form an equilateral triangle. But if you enter something like this in and it doesn't fit the triangle, the program will warn you that because of the particular bounds you've selected, you're going to have to switch to a non-simplex type design, which would be what we call an optimal custom design. All right, and this optimal custom design is set up to apply a criterion called I-optimality to pick, just the number of points you need to fit the coefficients for the model that you've chosen, which is quadratic in this case. And so you can see the 6 model points that are required. And then through a series of algorithmic exchanges, either coordinate or point exchanges, it sifts through a lot of possibilities to get just the 6 that you need. And then it adds a further number of points to fill in the gaps called check blends based on distance-based algorithm. And then it replicates a number of the ones that you've picked at this point to get a measure of pure error. So all of this is set up by default to make it really easy just to press ahead. then put your responses in. Now our responses were not very precise because this second response is called touchy-feely, and that was just a rating that we did on a 1 to 9 or 1 to 10 scale. So then when we finish, it's going to do the exchange and the point exchange, and it picks whatever exchange is best, in this case coordinate, and you get your recipe sheet. And we can identify the different points that we have here, where they're located. Now, what I would do in this case is I would use this round columns feature in Design Expert 13 so that we don't have so many decimal places here. And I would round this, maybe I would round it to only a 1/10 to make it easier to run. And then you would make up, your recipes that are shown here, measure the bounce of the play putty rolled up into a ball, do the touchy-feely rating, which is a 1 to 10, 1 being we don't like the way it feels, and 10 being we like the way it feels. Now I'm going to open up the results of this, and you can see that we got, by sorting this, a pretty good range in terms of how much it bounced, depending on the composition and how that reaction went for the cross-linking. And then for the touchy-feely, which is the way that you kind of pull it apart, you get a snap because of the dilatant aspects of it. That's what you're looking for, and we got some that came out pretty good in that attribute. Now the analysis of this, I'm just going to kind of skip ahead, but we're going to use a special type of model that's geared to the fact that the total is fixed and the response is a function of the proportions. It's called a Chaffee polynomial. And this kind of thing you're going to want to study. I would suggest, if you're not familiar with mixtures, if you go to our website, 3wstaties.com, and under Learn DOE, there's a lot of resources that we have available here. But if you go to Quick Start Resources and say, I'm a formulator, you'll see a little story here. What is mixture design and what's in it for you? A heads up from Mark Anderson, that's me. And we have this primer that we provide that helps you get your toe into the mixtures and kind of explains the aspects of it, because it's a little bit different. It starts with kind of a fun example of mixing gold and copper, and the old story of Archimedes, trying to check if the king's crown had been adulterated. And finally, when he realized that buoyancy was the key, he ran around yelling, "Eureka!" But he forgot to put his clothes on. Oh well. Anyways, if you look through that write-up, you'll learn a little bit more about this Chaffee polynomial. And then as we go through the analysis, it turns out that we end up with a pretty good model that diagnoses well. But the interesting thing is that these fit within these triangular spaces. Now, in this case, because the borax is a catalyzer, it's in there in very small concentration. So we get this very narrow track, relative to the other two ingredients. So it was kind of an interesting little experiment. The program has put in different combinations you can see by the red dots. And you can see how nicely this is filling out the space. So that's the analysis of the first response, the bounce. And then I'll just cut right to the chase on the touchy-feely one. And here's a contour result for that. Now what we can do then at the end, if we've got two decent models like we have, we can play off the bounce and the subjective touchy-feely results and try to get maximum bounce, maximum touchy-feely results. And this gives us our solution that tells you how much glue to put in, how much water, and how much borax, and going to the maximum level that we tried. Did the best in terms of barely getting, a bounce that we wanted. Now, I think for the actual commercial production of play putty, you'd have to do something a little bit more scientific. And you guys that are elastomeric and rubber scientists probably would come up with a better solution, or just buy the commercial product. So that gives you an idea of the mixture design. Any questions that you have, make a note, and I'll circle back at the end. And if you appreciate, play putty and being able to use mixture design to fool around with that, press that raise hand button. Good. Robert likes to have some fun. TK, Yun, et cetera, et cetera. Jorge, thank you. Okay, putting the hands down again. And I have one more, and that'll pretty much take up the initial hour that I was budgeting to this, but I'll hang on at the end, for a while and see if I can answer some questions. So the last one is a combination of things. It's a combination of different components that were studied for this aerospace application for a composite material. And then it also included, the two components that we have are here that are varied from 0 to 100%. So this is actually a mixture part of it. And these two are categorical factors. So that's the combination that we're doing. But then we had one other little wrinkle that's called a multi-component constraint. And you can enter in this multi-component ratio constraint into Design Expert in a special tool. And you can actually say that we want the ratio of C to D to be between 1.8 and 2.1 to try to keep that ratio of epoxy to hardener within a certain stoichiometric, ratio is really important to succeed with this experiment. This example is actually used in our mixture design for optimal formulation workshop, which actually I'm co-teaching this week at a distance. And if you can handle the English, I know that this is, could be an issue for some of our Latin Americans, but you are in a similar time zone. So you might consider coming in on one of our distance-based classes if you're interested in this mixture design, which would be really powerful for elastomeric, type processes and mixtures and formulations. So I'm going to close this design out that we had up there on the play putty. Now I'm going to open up another design that is this composite. And this is our recipe sheet, with the different weight percents of the elastomer fiber and so forth. And then the types are over here. And not sure if I brought in quite the right example here. This is actually a second one. I actually had two of them. The one that I want to bring in is a little bit simpler. So I'm going to actually go to the current class that I'm teaching and reopen another file that I have. Let's see if I can find that. That's a composite. Okay, here it is here. All right. Let's see what this looks like. Okay, this looks, well, maybe it's the same one, elastomer and fiber type. So we have epoxy and hardener. So I think my write-up isn't showing all the different ingredients. We actually had elastomer, fiber, hardener, and epoxy resin. So then the program, again, can handle this like it can handle just about any type of combination of things. But because it's a combination, there's actually two parts of the modeling. One is on the mixture and one is on the process, which is the categoric factors. And so we end up with the model. Now we're going to apply a specialized reduced model called KCV that makes it a little bit easier to contend with. And in the end, you end up with these mixture graphs that are affected by the type of materials you use, whether it's elastomer 1 or elastomer 2 or fiber 1 or fiber 2 or fiber 3 can make the difference. And then you do the same analysis on tensile, and basically the program will pick the model for you. And then in the end, you're going to do a numeric optimization to maximize, the two different responses. And the program will come up with some kind of solution. So that wasn't exactly what I was expecting from the slide, but it's a similar type of example that combines the aspects of mixture and process. And so that's that. So now I just want to wrap this up to say that hopefully via these different case studies, I demonstrated that multi-factor, multi-component tools are going to be very useful for the use in elastomer science and technology. Design Expert, certainly empowers you to make use of these tools because of its dedication to the use of the multi-factor tools. And ultimately, what it'll do is it'll give you a sweet spot, which are factor settings that meet all your requirements. And that sweet spot is going to be shown in the graphical overlay. So if we were to go back to one of these studies here, let's see if I can find something that works, that shows that sweet spot. Let's go to the vulcanization one, open that up again. And in the end on that one, we were able to see a numeric optimization for the two strength attributes. And then if you go to the graphical overlay and just say we've got to be at least 190 by the customer spec for the CS and at least 3.6 on the VDUL by the European standards, this is what I'm talking about a sweet spot. Now, as I change the temperature on this, the sweet spot closes out, almost closes out entirely. So you can see the sweet spot is very sensitive to the temperature for this vulcanization. So that's a really cool feature of Design Expert, to be able to see that. So I think engineers and scientists working in rubber and other elastomers will do well by applying these various types of designed experiments, the factorials that are good for screening and characterization, the response surface methods, which are called RSM for process optimization, and then the mixture design for optimal formulation, or some kind of combined design might be in order, depending on what you have in mind. As far as references are concerned, we've got 3 books. I'm the primary author of these that cover the factorial type designs in the DOE Simplified, and obviously the response surface methods in the RSM, and then of course the mixture design and this formulation simplified. And these are books that are available worldwide, via the internet from Taylor and Francis. We also have this training. I mentioned the mixture design class that is being taught this week at a distance. We also have one that's more focused on process that covers the factorials and the RSM. That's called Modern DOE. And these are available distance-based. I think we'll continue doing that, although we did that as a reaction to the pandemic. And we're starting to do some in-person classes. We found that the distance-based is over Zoom, works really well. You could also either in-person or distance-based, do some kind of private class that's tailored to your team. So if you're interested in that, contact our workshops team. So that's it then. If you have any questions at this point, feel free. That finishes up my regular presentation. Thank you for attending. And all of you that would like to head off now, feel free to come back and circle to the recording and just give me a hand wave as you leave. I would appreciate that. Just click that wave hand button. And then others that are going to hang on a little bit, if you want to type in a chat, I'll just hold on a second, a question or a chat. Let's see if anything pops up here.